All right, you guys, so we are going to use the square root method to solve quadratics. All right, I'm actually going to show you, I'm actually going to start you off by showing you what kids do wrong. And it just leads them into a disaster. So the whole point of knowing all these different methods to solve quadratics is to be the most efficient. So when I already have something squared for you, that's a gift. Take advantage of the gift. And here's what I mean. So I'll have kids that will write 9 parenthesis x squared minus 6x plus 9 equals 4. And then you get 9x squared minus 54x plus 81 equals 4. And these kids will try to go through and solve that problem using factoring. While it's true that that may work, and I say may for a reason, that is kind of defeating the point. I took this problem, basically. I took this starting problem and I manipulated it into this format for you so that it's time saver on your part. All right, so if you go through and distribute and multiply everything out, you just undid the steps that I did for you to make this problem easier to do. So it is, I can't emphasize that enough, it's a gift whenever you see something squared. Because it's ready to go. It's ready to solve directly without having to factor. I bypassed factoring for you. Here's the other thing. This answer may not factor. Okay? So if you get a square root answer, for example, let's say the answer to the problem, one of them is the square root of 3. If you try to factor, you're never going to be able to factor it. Because it's not going to factor nice and pretty. If something factors, it means you don't get a square root answer. So if this doesn't factor, it doesn't mean it doesn't have an answer. It just means the answer is a square root. So factoring is not going to help you. All right, so unless something's already like written all expanded out, I would never factor these problems. These are not expanded out for you for a reason. Rather, we're going to focus on isolating the squared term. So who's all being squared? The x and the 3, correct? The 9, however, is not being squared, so the 9 needs to leave. So if I want to undo 9 times this quantity, I would have to divide both sides by 9. All right, so those are gone. That leaves me with x minus 3 quantity squared equals 4 over 9. Here's the next thing. PEMDAS says I would have to subtract 3 and then square. Right? That's the order I read this problem in because the 3 is in parentheses. So if I'm going to reverse that, the first thing I'm going to undo is the square, not the 3. Right? The square was the last thing to be done, so it's the first thing to undo. So we have to take the square root of both sides. A square and a square root cancel each other out. Here's the catch though. Right? And I'll kind of divert off here for a minute. If I asked you to find me all solutions for that problem, a lot of kids would say 4. That's only half of the solutions. -4 is also a solution, right? Whether you square 4 or -4, you still get positive 16. So squaring is dangerous. Why is it dangerous? Because it makes signs irrelevant. So it makes your positives and negatives not matter if they're positive or negative because you get a positive answer after you square it anyway. But since you're working backwards, you have to keep that in mind. So here's what we do so that we don't forget about the negative version of the answer. When you draw a square root, again, when you draw a square root. Now, if I already drew a square root in the problem, you don't worry about this. I drew a square root in the problem. But if you have to physically draw a square root, then you also have to draw a positive negative symbol with it. So if anytime you find that you have to create a square root or you have to draw a square root, you must also draw a positive negative with it so that you don't make this mistake. All right, so a square root and a square, as we said, cancels each other out. So I'm just left with x minus 3. Okay, I don't have to worry about the positive, negative because I put it over here. It's going to take care of itself. I'm not going to make this mistake of forgetting about the negative answer. Now, we can do the square root of 4 and the square root of 9. You just square root the top and then the bottom. So you will get positive or negative 2/3. So how do you handle it from here? We divide it into two cases. Case 1, x minus 3 can equal 2/3. Case 2, x minus 3 could equal negative 2/3. Right, so I'm going to get two answers for this problem. This parabola would have two x-intercepts. So the first one would be 3 and 2/3. Now when I do the second one, all right, I would want to do positive 3, right? Move the 3 over here. 3 minus 2/3. Some of us can do that in our heads. Some of us cannot, all right? No big deal. But if you're not very good, well then change 3 into something over 3, like 9/3. 9/3 is the same thing as 3. So change it, and then you can go ahead and do 9 minus 2. You get 7/3. Or maybe some of you knew it was 2 and 1/3 from the beginning, which is great. Go ahead and write that down. Right. These are the two answers to the problem. So not only do they make the equation at the very beginning true, they're also the x-intercepts of the problem. So I'm going to go ahead, I'm going to erase my screen. I'm going to start fresh with letter B. So again, I already have it in a squared format. It's a gift. Work with the gift. Don't FOIL it all out. You're going to go crazy. First thing I like to do is undo this 1/3 by multiplying both sides by 3. And if you recall, we never put it inside the parentheses, only outside. Right, so that leaves me with 1. So I'm just going to write a minus 5 squared and 24. If you want to lose the squared, you must draw a square root. But the rule is, if you draw the square root, you also draw a positive negative symbol. So you can't do one without the other. All right, so then you're left with a minus 5 because the square root and the square cancel each other out. You have positive or negative. Now you can't leave it as 24, right? So 24 reduces square root wise into 4 and 6, which become 2√6. Now, 2√6 is not a nice pretty number, so that's okay. We're going to leave it alone. All right, all we need to do is just simply add this 5 over. So the way I present my answer is my 5 would now become positive, plus or minus 2√6. That is the way I present my answer, because I can't put 5 and 2√6 together. I can't make them into a number, so I have to leave them separated. So we'll just leave them as plus minus. So this is a problem that if you try to FOIL it out and use factoring to solve it, it is not going to factor. And the reason I know that is because that is an ugly answer. We can't just graph that spot nice and pretty on the number line. Because √6 is an irrational number. It never ends. So if you get an irrational answer, that means that you could not have factored to solve this, which is why we show you other methods such as the square root method. So another reason to avoid factoring if you have a square, a quantity squared in the problem. All right, letter C looks very, very intimidating. Okay, so the first thing we should train ourselves to do is eliminate the fractions by multiplying everything through by 12. So 12 times a fourth, that's 3. 12 times a third is 4. And then 5/6 times 12, well, the 6 and the 12 would become 2, and that would give me 10. Here's where I see kids mess up a lot. I'll have kids that'll do 3 plus 4, and they'll change this to 7. That is a PEMDAS violation. You're not allowed to do that. Technically, you would have to square and then distribute 4 and then add 3. So you can't do 3 plus 4 as your next step. Right? Rather than that, you need to focus on step 1, which was work on getting the squared isolated. So start removing things, not condensing, but removing. So we can remove the 3. That's gone. So now I have 4 times k minus 1 squared equals 7. Next, let's remove the 4. So let's divide both sides by 4. So I am in the process of isolating my squared term. Next step, if you want to lose the squared, you need to do the positive negative square root of both sides. So now I have k minus 1 equals positive, negative. Now, I can't do the square root of 7, so I'm going to leave it alone. But I can do the square root of 4, and that's just the whole number 2. So while I can't change the top, I can change the bottom. So when you square root a fraction, you're just simply square rooting the top and also square rooting the bottom. All right. Last step, to get k by itself, right? I would get 1 plus or minus root 7 over 2. So keep in mind, this exists on the coordinate plane. Like, you can graph 1 plus root 7 over 2. You can graph that. It's just a nasty decimal. It's a really ugly decimal, and it's not going to be a perfect graph, but somewhere out there it exists. Which is okay. I'm not asking you to graph it. That's why we use algebra, because I can just kind of tie it up with this nice, pretty symbolism. I can just leave it as square root of 7 over 2, and that's the precise answer to the problem. And again, since I have root 7 over 2, this is an ugly decimal answer, right? Which means if you would have tried to FOIL everything out and factor it, good luck. You're never going to be able to factor it because the answer is a nasty square root. So what I'd like to do to kind of do a little summary is, it says find all real roots, aka zeros, for each quadratic below. Now if you notice, these are all set up to factor, so I don't have like a quantity squared. So you can't really use the square root method for some of them. I will tell you though that in number 14 and 15 you can use the square root method. So for example, number 14, you can get this squared by itself. There's no p term, so you could totally do the square root method. So let's get the squared term by itself. 2p squared equals 80, right? I moved over the 4. Let's go ahead and divide off that 2. I get p squared equals 40. Let's square root both sides. So p would equal positive or negative, and you can't leave it as 40. You have to change it to 2 root 10. So factoring would not have worked in this problem. You would have to use the square root method because that's an ugly answer. You can't get that by factoring. All right. So keep that in mind for like number 15. All right. There's no k term. You can use that square root method. You can't use the square root method for number 12 though, because, well, you have an x squared and an x term. So you could lose the negative 5, but you can't square root both sides because you wouldn't square root the 6x. So that gets messy. All right. So trinomials, I would work on factoring those. Anything that's not trinomial, if you can't factor, then I would try applying the square root method. All right, so I'm going to actually pause the video, work up the answers to this, and when you're ready, you can unpause it and see how you did. All right, so don't forget, when we ask you to find roots or zeros, it means we put 0 in for y, and f of x is the same thing as y, so you're really just setting the problem equal to 0. So this factors nicely into x minus 5 and x minus 1, which would get you the answers 5 and 1. So those are the zeros of the problem. They're also the solutions to the equation for which y is 0. It means the same thing. All right, 13 also factors nicely for you, right? 7 and 3 are your magic numbers, so that would mean that x would be negative 7 or negative 3. Both of those are solutions to that problem. Number 15, I did not use factoring. In fact, if you try to use factoring, it's not going to work. So rather than that, we focus on getting the k squared by itself, which would get you the square root of 1 over 6. Now you can do the square root of 1, so I changed that to 1. You cannot do the square root of 6, so I left it like this. But it is considered not proper to leave a root in the bottom, so we change it to root 6 over 6 using our rules of rationalization. Right? And don't forget that when you draw a square root, you must also draw a positive negative. So you can realize, oh, a positive or negative version of this will suffice. Now number 16, you would have to factor because of the fact that you have an x squared and an x term in the problem. All right, so x would get, you would get x parenthesis 2x minus 3, so you only have to do a GCF. All right, then you can set each term equal to 0. So remember that whatever's out here in front, I could easily put parentheses around this x. It counts as a group, so that gets set equal to 0, and the 2x minus 3 gets set equal to 0. You get 3 halves and 0. And then 17 factored nicely again, so we get negative 7 and negative 2. Just two thoughts that I want you to consider as we wrap up this section of our notes. A function may or may not factor. Right? If it does not factor, it can still have real roots. Okay, so you don't want to say, oh, it doesn't factor, there's no solution. That's not true. It's just that your solution is going to be a nasty square root number. So you're going to have to use another method to solve. Factoring will not work. And then the other thought I'd like you to remember is that when you're finding roots of a parabola, you'll either get one answer, two answers, or no answers. And then I'd like to draw a picture of each scenario of what that looks like. So if a parabola has one 0 or one root, it will be on the x-axis itself. If it has two, that means that the vertex will be above or below. All right, and if it's above, it's going to have to be downwards. That way it crosses twice. And if it has no roots, if the vertex is, let's say, below, then it's going to have to point away from the axis, because it's never going to touch the x-axis, so this will have no real roots.